All right, today we are starting chapter 8. We are going to sort of combine sections 8.1 and 8.2. Just bundle them up together. So today we are going to use exponential growth and decay and its applications. All right, let's jump into it. Some notes about exponential functions. An exponential function is a function with the general form y equals a times b to the x power. When b is greater than 1, then b is the growth factor. When b is less than 1, b is the decay factor. So let's just think about this for a minute with some numbers. If b is greater than 1, give me an example of a number that would be greater than 1. 12? 7? Okay. 2? Some number greater than 1. We're calling it a growth factor. So that means overall, what do you think is what's happening to y? It's getting bigger. So every time we plug in a new number, y is getting bigger and bigger and bigger as x gets bigger and bigger and bigger. What about something that's less than 1? 0, a negative. What about something that's not 0 or a negative, but it's still less than 1? 0.5, a fraction or a decimal. A half, 3/4, 5/8. Okay, so we can come up with these other numbers that are decay factors, which means as we increase x, what's going to happen to y? It gets smaller, it goes down. So for growth, if x is getting bigger, y should get bigger. For decay, if x goes bigger, y goes smaller. We understand the general concept here? X is whatever we would plug in for x. So we'll be making tables pretty soon. Remember making tables, XY tables? And then x's, we kind of choose what we're plugging in for x, and then we figure out what the y's are. Okay. So let's look at some examples. We have to decide if these represent exponential growth or decay. Now I know you have it written on your notes right in front of you, but I'll put it up at the top of the slide. Our general form is y equals a times b to the x. So what are we focusing on? Which of these letters, y, a, b, or x, what do we focus on when we decide if this is growth or decay? India? B. Okay, our notes said that we look at b. Either b is bigger than 1 or b is less than 1, and that tells us growth or decay. So on this number 1 here, what is b? Which of these pieces is b? Charles? Okay, took it over for you. b is equal to 1.63, which makes this growth or decay? One person knows it? Oh, 2 people disagree. Is this number bigger or smaller than 1? Bigger, which makes it growth. So earlier when I said b being a decimal makes it decay, that doesn't mean any decimal or any fraction. It means ones that are smaller than 1. So if this had just been 0.63, that would have been different. On number 2, who can raise their hand and tell me the b? Jacob? 0.65. Okay, on this one, b is 0.65. After the comment I made at the end of number 1, hopefully we realize that this one is decay. This is a fraction less than 1.
So it's like the star number 1, like that. So every number under 1 would be decay.
Yes, 1 is the threshold. If b equals 1, then it's not changing. Okay, if b were to equal 1, this would just be flat line, no change. It would always stay the same. It would not get bigger or smaller. So I don't think we'll see that happen. On number 3, who can raise their hand and tell me the b? Charles?
1/5.
1/5. Good. This one's a little different because we don't have an A written out in front. What do you think that means A is?
0 or 1.
A 1. Okay, if there's not a number written there, we could always imagine there is a 1 out in front of that. Notice that b is going to have the exponent of x on it. B's got the exponent of x on it. So our b is 1/5. So we have to decide, is this going to be growth or decay? Decay. If we were to convert this into a decimal especially, we could see that this would be 0.2. 0.5 would be a fraction of 1/2. 1/5 is 0.2, which is definitely less than 1, so it's decay. On number 4, we've got y equals 1 over 100 times 4/3 to the x. Who can raise their hand and identify b? Emily? 4/3 is our b. Now this again can be a little tricky. Is this going to be bigger or smaller than 1? Bigger. If your numerator is bigger than your denominator, it's going to be bigger than 1, making this growth.
So you don't have to solve none of these problems.
Nope, there's nothing to solve. They just want to know growth or decay. I already gave this way a little bit, but the easiest way to graph an exponential model is to make a table of values. Here we go. It's been a while since we've graphed. We're going to have an XY table. Now, when we make these XY tables, we kind of get to choose what we're plugging in. In general, I'm going to need you to choose a negative number, a positive number, and I always recommend you use 0. Okay, so in general, you kind of get to decide, unless I fill in a table for you and say these are the numbers I expect you to use, you're getting to pick X. But to get a full idea of this graph, I generally, do I need a negative number? We definitely need to use 0. Let's start it off with 0, 1, and 2. I might not need a negative on these. I might be okay if we just stick with positives. Charles?
How do you know when you need a negative number?
If you have a negative.
If we were to be doing like cube roots, bigger exponents, if you know the exponent, like a cube root, a fourth root, a fifth root, we would definitely need negatives to get a good idea of the graph. But I think on these we can get a good idea if we start at 0 and we can see the shape of it. Of course, I definitely want 3 points on your graph, minimum 3 points. But I think we'll be okay if we start with 0. If I want you to do a negative, I'll let you know. All right, so we have to plug these numbers into x to figure out y. So here we're going to have y equals 2 to the 0 power. Anybody know what that is?
0.
No. No.
1.
1. Anything raised to the 0 power Anything, any number raised to the 0 power equals 1.
So 1,000 to the 0 power equals 1?
Yes. 10,000. 1,000,000 to the 0 power still equals 1. All right, on the next line, we've got y equals 2 to the first power, 1 power. 2 to the first power is 2. And on our last one, we've got y equals 2 to the second power. 2 to the second power equals 4. Now, I changed my mind about the whole negative thing, because if we were to plug in a -1, we would have gotten a fraction for y. And I just don't think we need to do that right now. So next comes plotting these points. Who remembers how to graph? Charles?
You go on the sideways axis, and then you put 0 in the middle. And then
I think you're on the right track. So left to right, we're moving 0. So we stay at the origin. Then what about up and down?
you go up 1.
We'd go up 1. So 0, 1.
Is it supposed to
It's
be
right there.
a straight line or something?
No, these will not be straight lines. We will see that in a minute. That's why we need at least 3 points, because if you only put 2 points, you might think it's a straight line. But indeed, it should not be. All right, who can direct me to the point 1, 2? Jacob?
Go right 1 up 2.
Right 1 up 2. And who can direct me to 2, 4? Devin? Right 2 up 4. Good. Okay, so we can see that this is not going to be a straight line. You can really see it even more if we were to go up again to 3. 2 to the third power is what?
6.
No, 8. So if we were to also plot 3, 8, you could definitely see this is not a straight line. Now it's getting bigger, quicker. That's what exponential growth does. It gets bigger, quicker every time. Charles?
Why do we have to graph these?
It's an important skill to be able to visualize the data. So you can see it getting big, quick. Okay, so then when we put our line in it, these are kind of going to be like when we did parabolas. It's not going to be perfect. I do expect it to have generally the right shape. So this one's going to curve up here, and it's going to be going down and down and down. Now, one thing that I want you to know is that this edge here, I kept it going the other direction because I could plug in negatives, but this is never going to cross the x-axis down here. Okay, this line would not ever cross that x-axis. The number will get smaller and smaller and smaller if we plug in negatives, but the y value would never come out to be negative. There is no exponent you can put on a positive number to make it come out negative. Does that make sense? Exponents don't change the sign of the overall number. Okay. We're all right with this first graph?
Yes.
Notice that I extended it in both directions. I put arrows on the ends. I still expect all of that out of you. And it's kind of got like a curved shape to it. On that last one, real quick, would that be a growth or decay? Growth. It's getting bigger and bigger and bigger. Our b was greater than 1. On this one, just from looking at the problem, y equals 4 times 1/2 to the x. Do we think it'll be growth or decay? Decay, because b equals 1/2. So this one, I agree, will be decay, so it should look different from our last one. Now, on a decay problem, using negatives might actually help you. But let's try without using negatives first, and then we'll throw in the negatives after. So we'll stick with 0, 1, 2 for now. And we'll talk about how negatives can help us sometimes. So for the first one, we've got y equals 4 times 1/2 to the 0 power.
1.
Careful. What's getting raised to the 0 power? The 1/2 is getting raised to the 0 power. So that part of it equals 1, but then we still have to multiply it by 4. 4 times 1 is 4. So this is 4 times 1. We end up with a 4. Next, we've got 4 times 1/2 to the first power. That's going to be 4 times 1/2. 1/2 to the first power is just 1/2. What's 4 times 1/2? 2. Next, we've got 4 times 1/2 squared. So 4 times. What happens when we square 1/2? What do we get? 1/4. 4 times 1/4 is 1. Now, if you're not great with, let's say, using exponents with fractions or multiplying fractions with whole numbers, you are, of course, allowed to use your calculator.
How do you do that?
It'll go a little quicker if you are familiar with it. Type in 1/2 to the 0 power and then multiply by 4. Or type in 1/2 times 1/2 and then times by 4.
How do you put in the 0 power?
That is something we will have to go over after notes. Use the little caret. Okay, let's graph these. How do I get to 0, 4? Okay, don't go left or right. We just go up 4. Who wants to help us with 1, 2? Ajaya? Right 1 up 2. And with 2, 1. Caden? Right 2 up 1. So you can still see that it's kind of got that curved shape to it. Again, it's not going to cross the x-axis. It's not going to jump down below that line. What do we notice about where x is negative? What's happening? When x is negative, what's happening to our numbers? They're growing. So if we were to use a negative exponent, remember a negative exponent flips a fraction. So we would end up taking 4 times 2 to some power. Okay, whereas if you are taking a whole number, raising it to an exponent, then you're turning it into a fraction. Okay, do we see how this one's getting smaller and smaller and smaller as we go? Whereas the last one got bigger, bigger, bigger. Are we ready to continue, or do we have questions about how we came up with these? Yes.
So if you go, if it's like facing, if it's not like a J shape, that means it's decreasing.
Right, the ones that looked a little more like a J were increasing. This one that looks kind of like an L almost is decreasing. Now, I don't plan on you having any sort of crazy graphs. I plan on you generally can use like 0, 1, 2. You're going to be able to show me how you got your coordinates. I do want to see this work over here. I want to see how you're coming up with it. I don't want to have you just write me a note. Used photo math. Okay? None of that. I want to see that you did the work to get your table. Uh-huh. Are we ready to go on to the back? Okay. This is what I consider to be the fun part. Not the filling in all these notes, but the applications. When you put money in the bank, the more frequently interest is compounded, the more quickly the amount in an account increases. The formula for continuously compounded interest uses the number E, which I know most of you right now are thinking, but that's not a number, that's a letter. Okay, in math, there is the natural number E. It is a thing. It's an irrational number, kind of like pi. It's approximately equal to 2.71828. All right, this is also referred to as the PERT formula because A equals P times E to the RT. A is the amount in the account. P is the initial principal amount. So P or principal, you might want to call that the starting amount or underline the word initial. They use the P because it's called the principal amount, but really, initial starting number. R is the annual rate of interest, and you need to know that that needs to be written as a decimal. You cannot leave it as a percent. It's got to be a decimal. And T in this formula is our time in years. Sure, the time is measured in years. Also notice that this is continuously compounded interest. At the bottom, we'll talk about the non-continuous. All right, let's practice using that then. So before we even get started, I'm just going to write this at the top. A equals P times E to the RT. If you have a scientific calculator with you, you might want to have it out. It's very hard to do these without a scientific calculator. All right, we'll read through the problem and then we'll start deciding what gets plugged in where to our equation. Suppose you invest $1,050 at an annual interest rate of 5.5% compounded continuously. How much will you have in the account after 5 years? All right. We're looking for how much we're going to have in the account. So amount in account, that's A. That's what we're looking for. A equals P is how much we start out with. What would that value be? The 1050. E is a natural number E, so we leave it as E. You'll often see it written kind of as a cursive E or an italicized E. R is our rate, interest rate, and I said to write it as a decimal, not a percent. So that means that just because we have a decimal, it still has a percent sign attached to it. So we still need to change that. Does anybody remember how we change this into just a decimal? You can type it in and press the button. There's a little bit, to me, a little easier way. Charles? Divide by 100, which moves our decimal point which way? To the left, how many places?
2.
2 places. So this becomes 0.055 times our time in years, 5 years. Now when you go to type this into your calculator, personally, I like to do it one thing at a time. So I personally would take 0.055 times 5 first. Okay, Okay, so I've got 1050 times e to the 0.275. Remember that this is multiplied to e. So what do we need to do next? Exponents or multiplication? Exponents. So we need to evaluate e to the 0.275 power. Now we have to find e on our calculators. Okay, so when I type this in on my screen on my calculator, which every calculator is a little different, when I press second ln to get to that e to the x button, on my screen it pops up e caret and opens a set of parentheses. Your calculator might not do that, but that's what mine did. And then I put in the 0.275 and then I pressed enter. Pressed enter after that. And then it gave me that 1.31. I'll just take it out to 653. Were we able to get there?
Yes.
Okay, if not, just give me a minute and I might be able to come around and help you out with that. Okay, then we still need to take that number and multiply it by 1050. So I don't even clear it off of my calculator screen. While it's still on my screen, I press times 1050. So my calculator says answer times 1050. And what do we get? Think a little more than that. 1,382. Since we're talking about money, let's go down to the pennies. And 36 cents. So if we're talking about money, I expect you to round it at the hundredths place. Take it down to the pennies. And that would be our answer. $1,382.36. So that means in those 5 years that we left all that money sitting in an account, how much money did we make? Just approximately. Okay, we made about $332, about $330, a little over $300. I just want you to be able to see we're not making $3,000, right? Like we started out with $10.50, now we got $1382.36. We made a little over $330. That's not a whole lot over the course of 5 years, right? But that's why you got to invest a lot of money to make a lot of money on it. All right, we're going to pause for a moment. One thing I want to mention, which I said when we were doing this, that I did not clear that 1.3 number off my calculator. I just pressed times right away so that it didn't round that number. If you round that number to something like 1.32, you might get a different enough answer that I would not accept it. Okay, now if we're off just a teeny bit from each other, because like maybe you rounded it off at the 5 and not all the way out to the 3 or something like that. Okay, if we're just a teeny bit off, that's fine. If you're dollars off or tens of dollars off, I'm not going to take it. So don't be rounding too much too soon. Does that make sense? One person thinks it makes sense.
Yes.
2 people.
Yes.
Oh, 3. Okay. All right. Are we ready to try another one?
Yes.
Yes. Charles is ready. Oh, I was not recording that. All right. Recap. We took our 0.076 times 1.5 to get our exponent of 0.114. E raised to that power gave us about 1.12075. Multiplied to the 400 gave us that 448.30. All right. Last formula for the day, compounded interest when it is not continuous. So this one looks a little more complex. It is. It does not involve that natural number e. So we again have the amount in the account is equal to P, the starting amount still. And then in parentheses, we have 1, just the number 1, plus as a fraction our rate divided by n. N, you'll notice, is the number of times our interest is compounded per year. Number of times it's compounded per year. So it could be compounded once a year. That would be annually. Could be compounded twice a year. If we were to compound it every 3 months, how many times would that happen in a year?
3.
Well, 4. Okay, remember there's 12 months in a year, so if it's every 3 months, that would happen 4 times in a year. So you could see these phrased different ways, and you have to figure out how many number of times it's happening in a year. We reuse that n as part of our exponent, same n, and multiply it to t, which again is our number in years, time in years. Suppose you invest $2,000 at an annual interest rate of 4.5%, compounded quarterly. So let's pause right there. Quarterly means how many times a year do you think? 4. So our n is going to equal 4. I might just make a note of that right away as soon as I see it. How much will you have in the account after 5 years? Okay, so we'll just worry about A first. I'm just going to delete B for a minute so we can focus on A. All right, so up at the top, A equals P times 1 plus R over N raised to the NT power. I just like to have that handy so I can see it and plug things in as I go. I'm looking for my amount in the account. Okay, so we start off with $2,000 in the bank. 1 plus, what is my rate as a decimal? 0.045 divided by, what did we say, n equals? 4. Raise that to the 4 times 5, n times t. Now, if we're following our order of operations, where do we start? No. In the parentheses. Good. So we are going to start in those parentheses. So if I take 0.045, divide it by 4, and then add 1 to it, what do we get?
1.01125.
Good. It's not that long. Don't round it. Just leave it alone. We can go ahead and decide what is that exponent going to be. The 20th power. So then this is going to be very similar to what we were just doing. Now, if you didn't have to use your calculator to take 4 times 5, and you still have the 1.01125 on your screen, you can go ahead and press that caret button and then type in your exponent of 20. So right now, my screen on my calculator looks like answer caret 20, and then I press enter. Now this number we'll probably want to round a little bit. So we've still got that 2,000 out in front times 1.25075. That should be enough decimal places for us.
Do I have that caret button?
Are we all good so far? Last thing to solve part A is to multiply. So again, that number's still on my screen. I just press my times button, 2,000, enter. So I get that A equals 2501.50. So after 5 years, how much money have I made? About $500, $501.50. I made about $100 a year, right? It's not terrible. It's a decent investment. Do we have questions about part A before we do part B? Yes, ma'am. How did I get 4 for n? So it said it was compounded quarterly. Quarterly would be 4 times a year. It's okay. We'll see some of those other words and we might have to talk about it, like biannually would mean how many times? Twice. Annually would be once. Trying to think of what the other common words are. Or they might just tell you
What is cube?
compounded 6 times a year. Biannually.
Try.
You won't usually see triannually now, but I suppose it's a possibility. All right, are we ready to knock out letter B? Can I erase all this?
Yes.
Erasing to bring back B. B says, if you save another $500 before investing, then how much will you have in 5 years?
3,150.
We just have to change the number.
We got to change the number. We can't just tack 500 onto it because we are then also investing that $500. So before we start investing, we save up another 500. So now what does our P become? 2,500. So now our P is 2,500.
Oh, and then we multiply by 1.
So we can still use the 1 plus R over N to the NT. That doesn't change. It's just that our principal amount went up to 2,500. So what was that decimal? 1.25075. Nothing else changed but our P. So all of that we took to calculate the 1.25075, that all stayed the same. So now when we multiply that by the 2,500, what does our final amount become?
3, 1, 2, 6, 8, 7. 8, 9.
I think it's going to be 8 is what I'm getting. Right? Because the 6 makes the 7 go up to an 8. All right. So we would end up with $3,126.88. So investing $500 more increased our profits by about $100. Right? We didn't just make 500 more. We went up to about 600 more. Okay.